Hello and welcome to my webinar on an introduction to ultrasonic assisted, uh, whatever you want to call it, droplet formation, atomization, nebulizer, spray technology. Um, so my name is Hussein Shakani, and I'm the founder and lead consultant of my company, Ultrasonic Advisors, and I'll be presenting this presentation here. The presentation is sponsored by PI Ceramic and I'll introduce how they might assist you with piezo ceramic materials for your specific application in this area. But today I'll be going over ultrasonic atomizers, droplet formation technology, why it is superior in some ways to other devices, other ways of making droplets, and I'll also talk about applications for this technology in general, and give you an idea about how to choose if you're in that arena. And I know maybe some of you are working in this area actively, and if you have questions regarding them, please put those in the chat. I think today is a fairly overview kind of topic, but hopefully I'll also add extra details based on my experience and also based on some of the different client projects I've done and what kind of problems are encountered in each of these areas. All right. So before we kind of get in further, just describing atomization, what is it? What are we talking about here? So basically, we're talking about the formation of droplets from a fluid, and a very basic way we can understand droplet formation is like you pour water out from a pitcher or a cup, and the stream of water becomes droplets. Now, if we control that precisely, make in micron size, and we're able to take ownership of that process, we can use it for many applications that I'll talk about. So we create mist, like a cloud, a fog, or a spray. The feeling or kind of interaction that we have is basically how large are the particles and how dense they are in the in the cloud or the mist. There's a couple of important points regarding this subject, so it's kind of vast. The topic of atomizers, there's like the very mechanical, physical part, let's say, of the ultrasonic area that I'll be speaking about, but there's also a lot of chemistry in terms of surface tension, viscosity, density. So surface tension, viscosity, and density are going to play a large part in determine what fluids can you atomize and as to what droplet sizes they'll become once you introduce that ultrasonic excitation or using other technologies. So these components really play a big role into what materials or what liquids you're able to atomize and what fluid sizes you need. So they all kind of play a part. So it's a very interdisciplinary area. And a lot of things need to be controlled at once. But thankfully, some ultrasonic technologies help in evening our ability to control the droplet size, which is really important. And so as an outline for the presentation, I'll be going over applications requiring atomizers, or basically droplet formations. I'll discuss the difference between atomizers and other type of atomizing technology. So this is a common thing that I see that people see or think that ultrasonics or piezoelectric devices, oh, it can be used in a certain area, but they kind of we forget about the traditional technology, like electromagnetic and other. In this case, the electromagnetic is not really irrelevant, but there's other there's other types of technologies that maybe seem a little bit more predated, you could say, but they still work extremely well. So we always have to kind of consider that the ultrasonic side or the piezoelectric side with respect to other methods of doing the same thing, which may actually be better in some ways. So there's three types of ultrasonic atomizers that I'll talk about, and you maybe could add one or two more, but these are like the industrialized, let's say, really commercially proven solutions, which is the mesh atomizing technology, the submerged element type, and the power transducer, which doesn't always end up being a lot of power, but it's in the configuration of a Langevin transducer, which many times are used for power applications like tens or hundreds, even kilowatt. But in this case, usually it's not going to be that high, and I'll explain why. This process simply doesn't require a lot of power. Um, how to choose a correct topology, and I think that'll be kind of obvious as we go through. And there are a lot of previous examples of applications too that you can kind of understand if your application fits in a specific category. And I'll describe some unique application of ultrasonic atomizers. So there's a lot of unique capabilities of ultrasonics, and it's being applied in a lot of new areas, perhaps with the classical physical principles, but with new applications. So I'll be describing that. So before we go on, I'll introduce the webinar sponsor, which is PI Ceramic. They're based in Germany, and they provide a lot of different piezoelectric material compositions. They're known to have, as it would describe, tremendous batch-to-batch consistency and reliability. Anyone who's worked in piezoelectric ceramics knows that the properties are variable from batch to batch, and to have a supplier who is both both does a lot of research in the piezo transducer area, as well as has a really strong reputation and quality control, and that's extremely important, especially for applications where those properties really matter, and you can't really afford as much variability as perhaps maybe other applications do. And of course, I'll introduce my consulting company, Ultrasonic Advisors, where I help companies to develop all different types of ultrasonic transducers, providing multidisciplinary support from electrical to transducer design and simulations. So there's a lot of services I provide. So please contact me through email or book a discovery call from my website in order to learn more. There's many different types of transducers I've worked on. In practice, atomizers are a common one. Uh, so usually the client has their application, but they're running into some issue regarding consistency, choices. They don't, circuit development and design and control, or there's other variability issues they're encountering, quality control of their output. So this is the specific atomizer areas is an area that have worked in and have practical knowledge of helping companies in. I've also worked a lot on bolt clamped Langevin transducers, amongst other types. So contact me to learn more and see if I can help if that seems like something you need. So here are the different applications requiring atomizers, and they're just a few. So I bulked one huge category into consumer. So this would be like you're inhaling atomized fluid. So that's obviously you think about medical, drug delivery through a mist kind of solution. There's also recreational. There's many companies, and if you thought of this idea, you're definitely not the first one. And it's been going on for a while about like replacing like tobacco with I think it's infused in some type of I forget what kind of material, some type of like alcohol material that typically the like the what is it called, vaping, those are using. So some companies are developing devices that can carry those substances in water. I guess it's more healthy. I guess hopefully while you're trying to quit taking those substances, it can assist you. So that's one common application or an area that people are working in. I'm not sure how successful it's been commercially, but that's one application that many companies are interested in. There's also comfort. This is the big one. I own several of these. Maybe a lot of you also own several of them, especially if you get sick, or even if you live in a cold area where you have your heater running a lot. Home humidifiers are extremely common, and that's probably the one that we all interact with the most. Like basically room humidifiers. I don't think home humidifiers use um yeah, somebody wrote propylene glycol for the vaping substance, like carrier fluid that's heated and then becomes I guess atomized or vaporized. So I don't think home humidifiers don't use uh like whole home, like furnace humidifiers don't use ultrasonics, but room ones do. So there's also humidifiers or like atomizers for beauty for I guess applying like like some type of substance to your skin um that would help. So there are companies doing that kind of development, and I think that technology has been commercialized, and it is it is available. Not necessarily like therapy, like the ultrasonics is providing the therapy. It's more the ultrasonics is providing the 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 topical fluid that's doing its job on your skin, I guess on your pores or something. There's a lot of industrial applications like in spray coating. Um, Here we have like a kind of a wafer and a semiconductor application where they need something sprayed on, like photoresist, for example, and very consistently, uh, without sputtering, with very high control. So ultrasonic spray technology does provide some of that. They're obviously probably more advanced and expensive types of equipment that can do it, but I think ultrasonics provides a specific niche for accuracy, efficiency, and consistency that other technologies would not be able to match. Um, there's industrial applications like in materials processing. When you spray this process of spraying material using ultrasonics, especially when you're sensitive to the surface and surface tension, and we talked about like viscosity and density, so that it helps to separate materials. That's a really big separate suspensions of fluid. One thing I'll talk about at the end is ethanol and water, separating those two fluids for development and creation of biological fuel for power. So that's an interesting application in agricultural, which is kind of similar to consumer comfort, but it's environmental control. There are also applications in ultrasonic drying. So sorry, the environmental control would be like a greenhouse. Yeah, creating the environment in a larger scale, without introducing heat or let's say a lot of airflow. So keeping the environment the same, but just simply adding increasing the moisture without changing anything else. So that's ideal there. In ultrasonic drying, there's both applications for drying of cloth material as well as drying of fruit. So fruit drying and food drying is I don't know if you would call it atomizing, but certainly it ultrasonics can be used to increase the rate or increase the effectiveness of heat when drying food. Obviously, heat is very expensive to create and to use for drying. So if there's, before you put before your clothes go from your washer to your dryer, the washing machine does extract as much fluid out as possible. If not, it would be extremely inefficient to put a load of laundry of really wet clothes in the dryer. So the similar case, it kind of helps with that drying process. It hasn't been used in consumer devices, but there's been curiosity and availability at times for that technology. So let's take a look at non-ultrasonic atomizers, because we know from working in piezoelectric devices, those of us who have and have maybe spent a huge amount of our careers doing it, we know they don't come without their problems of using ultrasonics. So it's not like we use ultrasonics whenever we can. There are applications where we would not want to for reliability concerns, for throughput, for power, for maybe this is a specific narrow niche that it's not going to work well for. So amongst so the different types of ultrasonic and non-ultrasonic atomizers, basically creating mist or particles from a liquid, is a high pressure stream which breaks up into droplets. That's you just shoot out the fluid from a nozzle and it just sprays into the air and just breaks up into particles, into droplets. There's also air atomization where you have a low speed fluid, but you have a high compressed air that again creates particles. There's centrifugal atomizing, which uses spinning plate, and I got these resources and pictures from this article here. So that's another way that particles are created. If you kind of see in this image here in the corner, it's pretty obvious when you look at it. And there's also electrostatic atomizing, where the liquid is charged and then there's a grounding plate, and the ejection of droplets happen due to the attraction or the repulsion effects in the liquid from the different chambers. So that also ejects fluid, but each of these either seem like they're very uncontrolled or very extreme, like how much voltage are you going to have to put to do electrostatic atomization. This seems, the centrifugal atomizing, like, okay, it's spinning around and it's creating these, how fast is it going to have to spin, and how, and it's non-directional. So there's a couple of issues here, you know, with the different methods, but they all have their specific places and applications. So here's a couple of features of ultrasonic atomizers that make them very attractive. They can be high throughput. They're so either individually or you can serialize them. So one submerged transducer is, let's say, 1 liter per hour, and then you get 15 of them. It's so you can now you just have 15 times or 20 times more throughput. A really nice part about ultrasonic atomizers is the relationship between frequency and particle size. So you do have a precise control of particle size, and in some cases, you really can't change the frequency on ultrasonic transducers. Why? Because they come with a resonance, and the resonance is of a frequency. So you'd have to do some redesigning in order to change any particle size development. That's perhaps the difference in these technologies, where, well, you just spray harder and you get different size particles, or you just change the nozzle really quickly and you get a different size particle. It's not as simple to change the parameters in an ultrasonic device, which relies on resonance. But you can redesign the device and approach any type of particle size you'd like, but it does take a redesign there. It requires lower viscosity fluid because it relies directly on that mechanical forced ejection from ultrasonics that other technologies would be able to overcome with different constraints and design choices that they have. The nice thing about ultrasonic devices for this application is that they're mechanically simple. They're just like the submerged transducer is a plate, is literally just like a piezo disc. The mesh transducer is a piezo ring and a mesh. The power transducer is a very classic Langevin transducer. It has multiple components, but it's certainly not, it doesn't have a lot of moving parts and failure points as other technologies might. In some cases, there's self-driving flow. This is especially the case in a mesh atomizer, especially if you're looking for a portable application where you don't want a lot of parts, you want everything to be very compact. These can be very compact, especially with the mesh atomizer. And I just put my logo here because I would be a logical choice to help you develop one of these technologies or troubleshoot them. Probably not so much these ones, although as a consultant, I train myself to talk about anything, whether I'm doing a good job or not. I'll just keep going. So there you have it. So here are the 3 types of atomizers: the submerged, what I'm calling the power. It doesn't necessarily have to be high power or higher power than others, and the mesh atomizer. There are domains which all of these 3 will be like a similar power level. And I'll mention the reason why these transducers don't require a lot of power is because they're not really, I guess a submerged transducer could, if you wanted to, have more power, but they don't require a lot of power because typically you're not doing a high power operation. So just making particles into a liquid into particles doesn't always doesn't require a lot of power to have that process happen. Unlike ultrasonic welding, for example, which is really well known for having high power devices like it can have up to kilowatts, or usually always start in the hundreds of watts, 100 watt for those type of transducers, typically. But for these cases, the purpose is to get liquid to become mist, and by driving more power into the system, you're kind of causing more irregularity and more performance degradation in terms of your particle size distribution, rather than just improving how well it works. So Oftentimes they're not actually high power requirements, but you can use them in serial. So let's talk about the submerged device. And we know this one. So I have several of these actually, just are several of these humidifiers. One, for every kid, every room, as everybody gets sick at once. So we have like a lot of humidifiers and to help with that. And I usually have lived in a cold area. So many of you might also. So this submerged atomizer. The element are just a flat disk. They can also be a hemisphere, but typically, especially for cost reasons, they're a flat disk. And they are submerged in a tank of water. And I'll just kind of show this here. They're submerged in a tank of water. Usually they're flat. They can also be put at an angle to increase the performance reliability. And an there's a column of water on top that has to sit. So the column of water is necessary because the transducer, even though it's flat, it's going to naturally focus its ultrasonic energy at a certain distance based on the frequency and what kind of fluid you're using, which is most commonly water. So if you see here the water level, so let me just make this bring to front. The water level versus the output, and you see it does change with different voltage levels. But let's say for this 48 volts series, as shown here, at 40 millimeters of water, there's the most missed output. This specific technology also requires that you have a fan blowing. It doesn't have enough ejection kind of power to blast or push the mist out of the chamber here. So you'll always have a fan, and kind of a hack for this little like home humidifier is to put a different, more powerful fan inside, so you'll get a little bit more like distance from your humidifier, because usually you've probably noticed that the air comes on and kind of drops right next to it. If you do install a more powerful fan inside, you'll be able to get that to go farther rather than like put it on the the highest dresser you can find. It tends to be a little bit more it tends to work better that way. So the focal points at the surface of the fluid, the high energy state ejects fluid. So we're not going to talk about the kind of the capillary waves and the dynamics going on there, but there's ejection at the surface. And the droplet size are controlled by frequency, but you don't get your control frequency typically. For these transducers, they work at the resonant frequency, so you'll have to change out your transducer for a thinner or thicker transducer if you'd like to change frequency. They're generally 10 watts to 100 watts for each element. And because they work in the megahertz range, you might find these transducers typically like the home humidifiers, like they're 1.7 megahertz, and we're not as picky with the droplet size and everything for like home humidifier applications. For example, so it's basically developed on practicality, rather than trying to get exact size and how well it doesn't drop to the floor, because you'd like that mist to go in the air rather than kind of wet the carpet or wet the floor. So the piezo element is directly facing the water in most cases. You can have more advanced applications where you have like a buffer fluid and other things like that, but generally it's in an interface with the fluid, so you'll have to have a coating. It requires balancing of the fluid. It requires a vertical orientation where the piezo element's on the bottom, then you have the fluid, then you have air. So the air is so often requires a fan. It's usually 1 to 2 megahertz, and the commercially kind of easily available ones are usually like 1.7 megahertz. And this is an ultrasonic fogger. What's sold is like a kind of a fogger, and that's kind of in a vat of water. And as I just described, if the fluid level increases or decreases, then there's going to be a change in performance. So it has an additional kind of constraint like that you have to control mechanically. The fluid level, which your home humidifier does, it has kind of like these valves and a water kind of float, which controls the fluid and if the device can turn on or not. The other type of device is a mesh atomizer. No, these have been very common, especially a really large interest area is in use of changing vaping, but it's also a nice kind of um device because so the way it works is there's a fluid behind, and I'll just draw this. So typically there's a fluid. So you can also just put fluid on top and drive it, but typically you have a fluid reservoir behind it, and the fluid is pulled through due to the vibrating. It's pulled into the mesh and then ejected out. So it's kind of nice. You have a forced ejection, which is of considerable speed, and it's good enough for medical like inhaling, and it's good enough for like a vaping substitute. So it does that is a good benefit. The nice thing about it is you can orient it sideways because it doesn't necessarily depend on the air interface because you have the mesh. So you can also do it sideways, and as long as you have a proper container, you'll be able to eject any direction you'd want. You can direct downward as long as there'll likely not be too much leakage also. So you can also do this like going. Oh, okay, all right, we got this. You can also do it in any direction. So that's a nice feature, especially for portable commercial applications. You want to decrease the components, and you have specific ways that you expect it to be used. Um, they are very oh, excuse me, they are very inexpensive. They're mass manufactured. The fluid is fed to the mesh either through a wick or through just a fluid cavity sitting at the back of the mesh, and so there's low leakage or no leakage depending on the mesh size. So it's almost like a valve, where you could just eject whenever you'd like to, and so you don't have to have an extra water containment kind of fluidic controls. You can even use this as a fluidic control to allow water to escape or be contained. So a mesh is attached to a piezo ring, and the fluid is in between the. There's an alternate application. So there's an alternate um, um, there's alternate method of applying. This method is that instead of having the fluid behind the mesh attached to the mesh and the piezo are separate pieces, and the fluid is actually in between. So you have the mesh, you have your piezo, and the fluid's in between. So then it's similar to like a submerged transducer where you're driving energy toward the surface or toward the air fluid domain, but you're not really driving it toward that area. You're driving it toward the mesh. So you're pushing the fluid out of the mesh. That actually makes the piezo construction more reliable, because of common failure point is cracking of the mesh element, debonding. That's a common failure point. So it does improve your reliability, but you're not as mechanically efficient because you're not directly applying energy to the mesh anymore, directly. So here's another view of that, where you have your transducer, your water reservoir, and you have an array of nozzles that the device would be interacting toward. So when the ceramic ring resonates, if you do have the mesh attached in the center, then it'll amplify that vibration. It'll bend up and down based on your resonant mode, but that's typically the mode that you're looking for, is to get the center. It's like you couple the radial resonance of the element with the mesh. So there's bending and there's there's some radial resonance going on as well in the ring. This creates vibration in the mesh and then can eject fluid based on the nozzle. And as you can probably imagine, the nozzle shape and the diameter and how thick this mesh is, that all of those things are going to influence the performance and the particle size and its variability, or its standard deviation. So it's great for a consumer project because it's inexpensive. It's self-contained in terms of its ability to eject fluid. It has low throughput. It's also not a high power device. And there is common failure modes like cracking of the mesh and debonding. those are true. And there's also a lot of variability. So if you've ever analyzed the impedance spectrum of these devices, they are very variable. There's a lot of spurious modes in these ring atomizers, and they're very hard to analyze in the traditional way that we're used to analyzing other transducers, because they have a lot of resonant, because it's based off of high frequency bending. They're about 110, usually they're between 100 to 200 kilohertz. And these frequencies are I couldn't explain it just off the bat, but they're ones that have been found to work, and they're kind of the classic um, usage frequencies of these devices. So they're 100 to 200 kilohertz. Um, and the nice thing about this, one of the really fascinating things about this is that the droplet size is changed by changing the mesh. So in this case, you don't have to change frequency in particular to get a different droplet size. You can't change the mesh, but you can build another transducer, about the same resonant frequency, but just different mesh to change that droplet size if you want to do experiments to determine which droplet size is best, or have similar drive circuits but different droplet sizes. So you could do that quite easily. However, for the submerged device, and what I'll talk about for the power transducer, where you're applying ultrasonics to more of like a thin layer of fluid, frequency is a huge player in droplet size. But here you can just change the hole size. Usually the mesh is metal. It's a metal mesh with laser drilled holes. And typically, you can get between like 1 micron and 10 micron hole size. As you get lower, obviously, there's more variability, and there's a natural shape to this hole based on your method of creating the hole. Um, so we'll talk about the power transducer for a little bit. It's a bolt clamped Langevin transducer. There's a through hole in the center of the transducer. Do I have a good picture of a transducer here? I actually don't. Anyways, that's okay. So there's a bolt clamp Langevin transducer, which is a piezo rings. There's a compression stack, and there's a horn. So the fluid is fed through the transducer to the tip, which is vibrating and where the atomization actually happens. So you do need fluidics, pumping fluid, not only keeping in the submerged case, you had to keep a constant fluid level. With the mesh atomizer, you just had to ensure that there's fluid being supplied to the back. And in this case, you actually have to pump fluid. And then turning on your transducer at the resonant frequency would then provide the mesh. Oh, sorry, then would provide um, the spray. And based on the unique thing about this application is based on the tip. The tip is flat or conical, triangular, different tip geometries, how wide it is. You can create a different plume, which is very nice for applying your spray material. Like if you're doing deposition or something, how do you want that plume, that spray to look? This is very well controlled by how you design your tip. In other cases, like the mesh atomizer or the submerged, you just get you get a cloud or you get a mist, but you don't have much control over what it looks like. You'd probably have to do further work to get the shape you want. You have to do other air fluid dynamics kind of related things. Here you get that by default. So that's a huge reason why it's used in industrial use, because you want that control. You want that as your specification. So in this case, liquid is pumped through the through hole. A specially designed resonating tip disperses the fluid, and the frequency and tip design determine the droplet size and the dispersion type, what the plume looks like. So as you can see here in this image, if you go with lower frequency, like 25 kilohertz, you get a mean droplet size of 39 microns. If you go with all the way up to 180 kilohertz, you'll get 10 microns. So we do know that 180 kilohertz is a bit higher than many normal ultrasonic devices, the power ultrasonic devices. So these are, as you imagine, going to be a little bit smaller. They don't require as much power, because your work is just a fluid. It's like a thin fluid. It's not like a huge kind of two large or metal pieces you're trying to weld together, there's much less power required. But as you might imagine, if you increase the throughput of water, you may have to like kind of increase the power. But I don't think a single nozzle for a large area is probably not the best thing for consistency either. So the happy medium is to use a bit of a lower power by normal ultrasonic standards and get the consistency. Um, So for reference, the both the submerged and the mesh atomizers are working in the 5 to 20 micron range, or lower or a little bit higher, depending on if you build something a little bit more unique. But this, as you can see, can go down to 39 microns, which is a bit larger, which may be useful for industrial use, but it's certainly not as good for putting mist out into the air and letting it kind of mesh with the or letting it absorb or mix with the air in the environment. It's more for depositing when you get to, especially when you get to the larger particle sizes. Um, so yeah, I'll now introduce some different interesting applications. So this is separation of water and ethanol from biofuel. So here's a submerged transducer, a solution of ethanol and water. And the ethanol molecules, there's a couple of theories about how this works, but the ethanol molecules are tend to be enriched at the surface, next to the vapor phase of the of the fluid. And ejection of the fluid at the interface contains more ethanol. So it's a way to separate these materials in a mechanical, like a low energy way, rather than a chemical or a more expensive separation mechanism, which might involve pressure and heating at the same time. So the nice thing about ultrasonics is there's no heating involved, at least directly, with ultrasonic atomization or evaporation. This is another really interesting application. So biological cell suspension processing. So this work, and I've done a little bit of work in this area in this specific device actually in my postdoc, which was a while ago. But it's an enhanced intercellular delivery via coordinated acoustically driven shear microporation and electrophoretic insertion. Basically what's happening is that there's a suspension of cells. They are being driven by a piezo transducer. So this is the mesh atomizer that's not combined. So the transducer is separate from the mesh, and it's driving these cells through the hole, and due to shear forces, they're becoming porated. Their cell walls or their membranes are becoming porated, which then allows scientists to do additional tests and manipulation of the internals of the cell without having to do chemical or other types of methods to get that to happen. So they can it assists them in studying of cells and the other processes there. And here's one. So ultrasonic coating for semiconductor applications. So in this case, it's going to provide a very highly uniform coating, for example, for photoresist, and there'll be a lot less wasted material. So it's not only that the accuracy, but what you gain with accuracy is you can use less material and you get a better final result. And you also are able to control process parameters. That's really that's really exciting in order to control the output, and you can change nozzles, and you can have a bunch of different mechanisms by which you use ultrasonics in this case for spraying. In this case, you can tell by the shape of how this transducer looks. You can just tell the tip, right? Because you can't tell the stack inside of the transducer. That's usually hidden, or it's usually kind of mounted. But this is just the tip, so it's the Langevin or bolt clamp transducer being used in this case. Kind of as a summary of these technologies, the submerged transducer works usually between 1 to 2 megahertz. It's 5 microns to 15 microns. Each element is 10 to 50 watts. It's often used in multiples if you're using it for industrial application. Its typical uses in kind of room humidifier for the consumer, fogger, or basically environmental control. and it focuses ultrasonic energy at the fluid-air interface, and then if the fluid ejects, the energy ejects the droplets from this interface, the surface. For the mesh atomizer, the frequencies are between 100 to 200 kilohertz. And these are all resonating type, by the way. So they're 5 microns to 10 microns. And the nice thing about this is that changing the hole size match strongly influences the particle size, which is not true for the bolt clamped or the submerged case, where you don't have as much independent control there. You have only control with frequency, which you don't have control over because you design your device for that too. So mesh atomizers typically are 1 watt. They're low power. They're most often looked at for battery powered applications, or where you don't want to put another fan. That's or or the orientation can be sideways, but it's usually not for moving a lot of fluid. So it's also very compact due to not requiring a fan or a lot of mechanical assistance to get its job done. So fluid is pulled through the vibrating mesh and ejected out as atomized droplets from the holes. And the bolt clamped transducer may work between 20 kilohertz to 120 kilohertz, depending on your design again. It has 10 to 40 microns of particle size, and I just kind of pulled that from this plot here. The power is 10 to hundreds of watts. I didn't find many specs online for this, but obviously, depending on if you're using a 20 kilohertz transducer with higher throughput, then you'll need to use a higher power. But spreading that fluid out over the interface, you may be limited with some other processes. You don't necessarily always get more throughput just because you put more power. There's other things limiting your application. But maybe if any of you would like to develop a higher power or a different type of transducer for this area, I would be a great person to work with. The typical application is industrial. I'm not aware of any consumer applications that use a bolt clamp transducer for any consumer use. So the fluid is fed through a vibrating tip and atomized there. And the tip style governs the plume shape, which is obviously super useful for ultrasonic, super useful for industrial spray coating and related processes. So with that, I should have probably had a question slide. I'll take questions, and I will stop this recording.